Hello, I'm Ethan. The paper I'm going to talk about is Smart Grid Energy Management using LSTM, a deep learning-based approach. So the paper addresses the challenge posed by the increasing energy demands globally, which have put significant pressure on traditional power grids to maintain a balance between supply and demand. A smart grid is introduced as a modern solution to this issue, offering bidirectional energy flow between utilities and users. Smart grids utilize advanced technologies, including sensors and actuators, to enhance load balancing and peak shaving, which are critical for efficient energy management. The emergence of smart devices in smart grid environments generates vast amounts of data related to energy usage and user behavior. And this data is essential for effective demand response management and load forecasting. The paper identifies the challenge of managing high-dimensional big data generated from smart grid system. This data is collected from various smart devices and includes attributes like energy consumption, voltage, and appliance usage. A significant issue is the need for efficient data representation and pre-processing. Dimensionality reduction is highlighted as a critical phase in data pre-processing. The paper employs high-order singular value decomposition to reduce the complexity of the data while maintaining essential information. Ultimately, the main objective is to minimize prediction errors in energy consumption forecast. The paper emphasizes the importance of preprocessing the collected data from smart grid system. This involves steps like data normalization, interpolation, and removal of duplicates to ensure the data is clean and ready for analysis. High-order singular value decomposition is applied for data decomposition. This technique reduces the dimensions of the data while preserving essential information, which is crucial for effective analysis. The core analytic technique employed is the long short-term memory model, a type of recurrent neural network. LSTM is chosen for its ability to handle time series data and mitigate the vanishing gradient problem, allowing it to learn long-term dependencies effectively. The model's performance is assessed using metrics such as root mean square error and mean absolute percentage error. These metrics help in quantifying the accuracy of the energy consumption predictions. And next, I'll briefly explain how LSTM works. LSTM has a cell state that acts as a memory, capable of carrying information across long sequences. It helps in preserving important information throughout the processing of the sequence. It uses 3 gates to control the flow of information. Forget gate decides what information to discard from the cell's state. It uses a sigmoid activation function to output a value between 0 and 1, where 0 means completely forget and 1 means completely retain. Input gate determines which new information to add to the cell state. It has two parts, a sigmoid function that acts like as a gate, and a tank function that creates a vector of new candidate values to add. Output gate decides what the next hidden state should be. It uses a sigmoid function to determine which part of the cell state should be output. The cell state is updated by forgetting some information and adding new information. The hidden state is updated based on the output gate's decision. The dataset utilized in this paper consists of energy consumption data collected from smart building over a period of 500 days with a sampling rate of half an hour. This allows for detailed tracking of energy usage patterns. The analysis incorporates data from 112 households, providing a comprehensive view of energy consumption across different environments. In addition to energy consumption, various external environmental factors are considered, including visibility, temperature, wind speed, wind bearing pressure, and cloud cover. These factors are crucial for understanding the influence on energy usage. The data is pre-processed and merged with weather condition data before being analyzed using the LSTM. This preprocessing includes cleaning, normalization, and dimensionality reduction techniques to enhance data quality. In fact, there are not many results written in this paper. In the results, both RNN and LSTM are only ran for 50 epochs. As can be seen from the figure, no matter which iteration it is in, the RMSE score of LSTM is the lowest. And in the table, the RMSE of RNN, ARMIA, and LSTM are 4.613, 4.27, and 3.35 respectively. And the MAPE are 70.312%, 29.18%, and 5.21% respectively. The following figures show the actual value and the values predicted by the model. So as you can see that although they feel very close, I think this is still not accurate enough for the power grid.